All right, it's time for 2.4, which will be going through a library of functions as well as piecewise defined functions. Stuff you've seen before, but definitely need to review it and expand upon it a little bit, which I love doing. All right, first off, let's go through our library of functions. We've got a handful here, to say the least. The first one here, what is that? That would be our identity function. And our equation for that would be y equals x, or you could write it as f of x equals x. Okay, excellent, wonderful. For ease going forward, I'm going to go ahead and just write y equals, okay? But it can be written in function notation as well. The next one, that is a quadratic here, what we call is the square function. Lovely. So that would be y equals x squared. The next one here, the cube function. That'd be y equals x cubed. If you'd like to go ahead and try this on your own, hit pause, see if you can remember all of them, and then let it play through, all right? It's always nice to test yourself. The next one, we have the square root function. Does not look like any. That's a little better. And that would be y equals the square root of x. Cool. Fantastic. All right, we're down into the next one here. What do we have here? That is our cube root. And that would be y equals, and then we'd have our radical with a little 3 right there. Awesome. Next one we have is absolute value. Absolute value. All right, and that'd be y equals absolute value bars. Boom. Dunzo. Excellent. The next one, we have an exponential growth function. There's also exponential decay, but for this one, we'll just do the growth function so we don't get too overwhelmed here. Exponential growth. All right, and that would be y equals b to the x. Oh, losing the light. And that is when b is greater than, ooh, voice crack. I'm leaving it. B is greater than, not 0, 1. All right, so when that base is larger than 1, we have a growth function. Excellent. Okay, and the last one, that is our reciprocal function. Reciprocal function, and that would be y equals 1 over x. Woo! It's quite the library there, I'll tell you what. So although we have a pretty robust library at this point in time, we actually have one graph that we left out. That is the constant function. Why might that be? Well, the reason why we did that is because there's really an infinite amount of constant functions, so we didn't want to give one particular graph and say, like, this is it. So let's go into an example. A constant function is just like a y equals, say, 3 or 2 or any real number. So really it's y equals b, where b is any real number. And an example of a graph would be something like this. I'll change marker for the actual graph. Just when I said y equals 3, 1, 2, 3, boom, that would be 3. All right, so it's a horizontal line. That is our constant function, right? Y equals some number, any real number. Cool. All right, so now that we have our whole library, right? Let's start looking at piecewise defined functions. So a piecewise defined function is when a function is defined by different equations on different parts of its domain. That's when it's called a piecewise defined function. Lovely. Again, you've seen these before a little bit, but we're going to work with some here and probably ask a few different questions than you're used to. So this piecewise function is defined as what we have here, right? 3 different parts. So we want to find f of -2, f of 0, and f of 3. So let's go ahead and do that. Well, how am I going to find f of negative 2? Let's start with that. Well, if I'm doing f of negative 2, I can't just plug it into any one of them. I got to find that one that fits its domain. So here I would have x is less than 0. That would fit, right? Negative 2 is less than 0, so I'm going to go ahead and plug that in here, which gives me 4. So there's my answer for that one. So let's see here. How about f of 0? Well, if I plug in 0, which one has the domain that would include 0? Well, that would be the one that says x equals 0. So that means it's just 2. That's a constant function portion of that. All righty. And then lastly, f of 3. Well, let's see here. The one that's greater than 0 would be the one that would include 3 in its domain, right? So I'd have 3 plus 2, which equals 5. So I just substituted it in there. We're good to go. Part A done. Excellent. All right, so now determine the domain of f. I often find this a little bit easier to do after I've graphed it, but we'll do it here, and then we'll also talk about it on the graph. So let's see. I have less than 0, so we know that x is less than 0. We know that it's equal to 0, and x is greater than 0. So that actually includes everything. So we're really talking negative infinity to infinity. There are no gaps in the domain. Now, if this equals 0 part was not here, it would be negative infinity to 0, not including 0, and then pick back up, not including 0, to positive infinity. But because it has every x value, it's all real numbers, negative infinity to infinity. So let's go ahead and graph this, and we'll also look at it visually. So I like to pick some points when I'm doing this here. So first I'm going to pick 0. So 0 squared is going to be 0. And then another point on this quadratic, less than 0. So how about negative 1 would be another one. So negative 1, if I plug that in, I get positive 1. And if you wanted to do another one, we could do negative 2, and then we'd get positive 4 as our output. Actually, we already did negative 2 plugged in, so we should know that. All right, so I'm going to go ahead and plot this portion of it. So I put in 0, 0. That is an open circle when I graph that, right? And then I'm going to have negative 1, 1, and negative 2, 4. And you may have known just how to graph this because of our library of functions, but I think points often help, and I will do my best. All right, that wasn't too bad. Cool. So there's our first part of the graph. Lovely. Now I'm going to do some different colors here. You don't have to do that, but just to showcase the different pieces of this piecewise function. So we'll do this next one in blue. So it's just when x equals 0, our output value, our function value is 2. So it's just 1 point right there. That's it. That's a closed circle. Cool. And then the last one we'll do, I'll go with green on this one. So again, I'm going to have to substitute in some points. So I'm going to plug in 0, but remember 0 is not a point on this. It'll be an open circle for that. So if I plug in 0, my output is 2. If I plug in, let's say 1, and we know this is a linear function, so it's just going to be a straight line. If I plug in 1, I'm going to get 3, and we can really stop there. With the quadratic, I like to have a few points to show the curvature of it. You may, again, have known just the shortcut, you're counting up, and that's fine too, as long as you're getting the right thing. So I'm going to plug in the point 0, 2, all right, which is right here. So I have an open circle around that. Let me get a little closer. And then I've got 1, 3, and since its slope is 1, from our knowledge of linear equations, we can just go up 1 over 1 and whee, just like that. Excellent. Wonderful. Cool. Yay. That was pretty awesome. So we've graphed it. Happy. Now, let's talk about that domain as I try to recenter this. There we go. So that domain, now we can see on the graph, well, it keeps going up and to the left. So it's infinitely going to the left. It's infinitely going to the right. And there are no gaps because you have this solid dot here where there were the open circles. So it's all the way through. Cool. So negative infinity to infinity. All righty. Now we're going to use the graph to find our range. So a range, where does it start? What's the lowest it goes? It looks like it goes all the way to 0, but does not include 0. So we have 0. Well, that's the end of third period. And then does it ever stop going up? Does it have any gaps as we move up? We're solid here, and it keeps going up. It goes to infinity. Awesome. So this is not like some kind of a break here now, because we have this function in pink, or this part of the piecewise function in that pink color that would, bridge that gap, so to speak. So we're from 0 all the way to infinity. Lovely. So just to reiterate about that comment about the range, about that jump, that is a common misconception there that people are like, ooh, yeah, I got to take that out of my range. Okay? There's graph going on there. So is f continuous on its domain? That's a good question. In this case, no. We have what's called a jump discontinuity. It comes down the parabola as we're moving from left to right, jumps up to that single point, right, in the constant part of the function, and then goes into our linear portion of the function. So jump discontinuity. Sound it out. There we go. All righty. Wonderful. All right, so we're going to just do one last problem here. Only 2 examples. They are pretty large examples, though. This time we're given the graph. We're going to write the piecewise function whose graph is shown, and then we'll do the same type of questions. Looks like we got one different one with the locating the intercepts. All right, let's do it. So let's start with our function here. These are always fun to write. My favorite. I'm going to go from left to right. I would suggest you do the same. So here, if I'm starting with this portion of the equation, I'm at -3, 7, and we got ourselves a linear equation, right? And let's see if we can see that slope there. It looks like it's -2, down 2 over 1, down 2 over 1, down 2 over 1. Yep, okay. So I have a -2 slope. And then what's my y-intercept? That is +1. So -2x plus 1. And then where are we defining this? This is between -3 for my x value all the way to +1. So from -3, including that, to +1, not including that. Okay? First one done. I like it. And actually, rather than a comma here, I'm going to go ahead and use if. My apologies there. Use the if instead of that comma. All right, the next one. Looks like we have ourselves just a point there, kind of like the last problem. So when x equals 1, our output is 2. So this would be a 2 here if x equals 1. Awesome. And this last portion here, well, it appears to me to be a quadratic. Okay. And perhaps maybe if we had, I think we should have had one more point in there. I'm going to go ahead and add that for us. Okay, I added this point in here. I feel like it should have been there to be a little bit more clear that it's not a constant rate of change, right? So if we're going, when we see going up 3 over 1, then up 5 over 1, that clues us into that quadratic, which would then appear to then, if it were to extend, it'd be at the origin there. So that is going to be our parent function for a square function. So we have x squared if x is greater than 1. It is an open circle, so it's just going to be greater than 1 there. All right. So it really helps to know those parent functions, the behavior of those functions, so we can look out for those. I think the lines and the points are always easy to see, but once we get into a square function, your quadratics, your cube functions, so on and so forth, it really helps to know what they look like as we're trying to write that equation. Very challenging otherwise. But this looks good to me. So let's move on. Let's find f of -2. And I can either do that from the graph or I can do that from the equation. Since we did it from the equation before, let's do it from the graph. F of -2 would give me 5. So I went and just found that point on there. And we could verify that here. -2 is within this domain. And if I plug -2 in here, I'm going to get +4 plus 1 is 5. Alrighty, f of 1. Well, where's that going to happen on my graph? That's right here. So boom, 2. And if I have f of 2, that's going to be right here, which has the point 4. Great. So you use the equation, the piecewise function equation. We can use the graph. we can use both. It's good to be good at both. All right, determine the domain of f. I like using the graph when I find domain and range of a piecewise function. So farthest I go is -3, and I'm including that point because it is solid. And then as I'm moving to the right and going down, I do have it looks like another jump discontinuity, but I do have this point here, so it's continuing through and goes on forever and ever and ever to infinity. It continues moving right. So there's my domain. How about some intercepts? Well, how about let's start with our x-intercept. This one is actually a little tricky. It's between, but I think we can figure that out, that is going to be at the 1/2 mark there because of our slope that we have, which was -2. So it's going to split that right in half. So x-intercept is going to be 1/2, 0. And then our y-intercept, we already talked about our y-intercept of our first equation, part of our equation there, and that would be at 1. So 0, +1. Awesome. So how about our range? We're going to use the graph to find the range. Well, how low do we go? We start at -1, not including -1. And then it looks like we go on up, just like the last one. Yeah, this still is part of the graph, so we don't have to skip over anything. And over here it goes on forever and ever, ever up, right? It does stop over here, but this graph is continuing on forever. So we go to infinity. I love it. Excellent. Wonderful. The graph really, really helps when we're talking domain and range, in my opinion. Is this continuous? Once again, we have that jump discontinuity at x = 1. So no jump discontinuity at x = 1. So it's not continuous on the domain. That is it for this one. I hope you guys enjoyed it. I know I sure did. And I will see you guys later in the next video, in class, all over the place. Who knows? All right. Have a wonderful day. America, freedom, rock and roll, Costco. And Riverdog Jenny on the gram.